Posso start.
So very good morning to all of you. So we are again meeting here on the day number 4, right? 4th day. And we are now to start the session 10 by our expert speaker, Professor Alberto. So sit and enjoy the session.
So 4th day and still alive. So that is already a success. We try also today. It is, I will keep this lecture of 2 hours. I will try to show something, but please feel free to interrupt me at any time if you have questions or also comments and say, no, it is not so, you are wrong, something like this. The first part is, I can also give you an overview of all the thing of this morning. I put at the beginning something, the focus here is on the grid rather than on the users. And how can also the users, the final users, helps for the operation of the network. So the focus is on the grid. So I will try at the beginning to show a model that represents a possible operation of the distribution network with many users that have some generation, so distributed generation, in particular renewable generation. And then the focus shifts a little to charging station. We see that in the future they are expecting to use many vehicles, electric vehicles. So probably there will be parking lots with many charging stations and also some importance. No? So we have considered a futuristic view of parking lots with this charging station with 50 kilowatts and how to operate the network, avoiding congestion, so reduce the congestion, the effects of these parking lots without doubling or multiplying the capacity, the distribution of the distribution network. And in the second hour, I will try, if you agree, to focus on the voltage control in the distribution network. And the last part of this morning will be devoted on the operation of the charging stations, of the parking lots with many charging stations, not as we need to protect themselves from their charging, but how they use, because several cars are connected to the charging station for several hours, so they can also provide some service to the network in order to be treated as a flexible load, so we can require to decrease or increase their consumption during the day. I will start with the first one, is I will start. probably it is. Okay, so this, thank you. Oh, perfect, it's working. This one. Perfect, yeah. And also, perfect. The impact of renewable energy generation. So 2 topics, short-term scheduling of active distribution systems. Active because there is a generation inside, active because also the operation of the distribution network needs to be active, not to control many things inside. And focus on voltage optimization, and the second is the one that I mentioned. So the idea of the coordinated operation and management distribution network in presence of high penetration of distributed energy resource. This is the title. So this is the figure that probably we have in mind when we are looking at this operation distribution network. So we start with a more detailed state estimation. In the past, probably the only direct measurement in distribution network were the current at the substation. And then now we need to understand better what are the voltages and currents also in the feeders, along the feeders, and also estimate, of course, this state estimator is very different from the one for transmission network. In general, for transmission networks, we have more measurements than the variables. So it is the problem of combining the measurements from different sources and have an overview of the network. In distribution network, in general, we have less measurement than the things that we want to know. So it is the problem to recognize also the things that we are not measuring directly, because we cannot measure the voltage in every node of the distribution network. That is too much. Then we need to have some forecast, and this is the important thing. So forecast, I know that many of you work on forecasting many things, energy production, the load profiles, and the renewable production, and both for the day and also short time. We said here 1 day and 15 minutes ahead. So we have here a first problem that we can mention here, scheduling of the day ahead. So the day ahead we can prepare some resources in the network in order to cover the load, and then we propose here in this scheme intraday scheduler, and I will focus on this. Intraday scheduler that every 15 minutes adjust the operation of the network, in particular in order to keep the voltage stable into the network, to optimize the voltage profile. The intraday scheduler acts in general to the on-load tap changer, or LTC, so the possibility for the transformer to change the ratio of the operation during the day, and also some local control, capacitor banks, but in particular we think that the distributed energy resources can be controlled, so we can change in particular for the voltage, the reactive but also the active power of the available resources under the control of the distribution system operator. If you like the idea, we can also, here it is just, it is written what I've tried to say already. So the day-ahead scheduler calculates in general, the most economically convenient set points for each distributed energy resources. And in the example, we have considered also electrical, the forecast of renewable energy resources, energy cost, the limits. So these are all the inputs for this problem. And the intraday scheduler can typically act every 15 minutes and updates the set points of available distributed resources. So I will focus on this, and this is the idea behind this intraday scheduler. And for this we have used a three-phase power flow that is a separate tool from the procedure. And here we have used EMTP as a tool for calculating the three-phase solver of the power flow in the distribution network. Why three-phase? Because probably the distribution network, another difference with the transmission is that the imbalance and also the not perfectly symmetrical configuration of the conductors are more significant than in transmission network that is in general more balanced and also symmetrical in the operation. So there are we use this three-phase power flow, and from three-phase power flow we can calculate also the sensitivity matrix. So what are the sensitivity matrix? There is also a slide for that. It is, the sensitivity on what we need to control, for example, the voltage with respect to injection of active power or reactive power, so variation of the active and reactive power in the various nodes, or the change in the tap changes. So how vary the voltage in one bus, because bus I, because the injection of active and reactive power in bus J is varied by a small change, a small delta. I will try to show you that this relationship between variation of the control variables and variation of our variables here, the voltages in particular, but also the current in the branches, can be directly calculated by the results of the power flow. In particular by using the Jacobian matrix, that in general it is used by the solution of the typical three-phase power flow because it is Newton-Raphson, so it is in general included there. So from this matrix, by using this matrix, we have a relationship between what we need to control and our possibility to control, so the control variables. So we can solve a problem that is, with a simple structure because it is linear. So it is a linear programming problem with some integers because the number of steps in the transformers is not continuous, so can be represented by integers, and also some other variables can be represented just with a variable that is 0, 1, not in the middle. No? In this way, we can calculate for each 15 minutes what are the adjustments. So how much I need to change the power, the active power, the reactive power, and the tap changes in the transformer in order to achieve a better profile. For example, the voltage or the constraint. In general, this calculation gives just an indication of the direction. So in order to speed up this, that is a iterative procedure, we can multiply also these delta x that are these control variables for a factor, no? So an accelerating factor or decelerating. It means that if it is larger than 1 or lower than 1, in order to speed up the convergence. And this factor can be obtained by the solution of a nonlinear one-dimensional optimization problem, just iterating with the calculation of the power flow. Here we have in mind that these three-phase power flow algorithms are very efficient. So in fraction of seconds, they do all the calculations. So we can apply this possibility, in order to run several times automatically, and obtain the results fast enough in order to keep the time. That is, for us, it is 15 minutes. So we need to update our decision every 15 minutes. So I would like to say some details about this model. The model is the minimization of the deviation of the power output set points. So the first one is the fact that we have already calculated something optimum, no? The head. So we need to keep in consideration also this result. So we in the objective function we minimize the deviation with respect to what we have decided the head. Obviously, if we keep just this, it is not needed. We don't change anything with respect to the decision of the first day. So we put in the objective function a factor here, alpha, and there are also beta and gamma, and the summation of the three is equal to 1, so it is lower than 1. And in order to weight this objective, because there is another objective in general considered, that is the minimization of the losses, so we include also the minimization, or we can include the minimization of the losses, and in particular, this is the focus here, it is the minimization of this S, that is the absolute value of the difference between the voltage in the bus and the rated value of the voltage. So we try to keep a constant profile. This minimization of the absolute value, it is linear. So you can see the linearization, typical linearization, because you have this variable A, that is the modulus, and you can put this S greater than 0, A minus S minus lower than 0, and you see that if you minimize the non-negative slack variable, you obtain the absolute value. So I will try to see also the linearization. This is the linearization that I was mentioning before, so these are the constraints of our problem. This is the modulus of the voltage that is given by this K, and this K are these sensitivity values that we have obtained from the power flow calculation, and they are the link between the voltage variation in a bus with the variation of the power, active and reactive power, of the distributed energy resources, and the number of taps in the tap chains.
On-load testing.
Yeah. Also the same we can see for the losses. So also for the losses are depending on the current, so also the current can be related with the coefficients, the sensitivity coefficients with our control variables. In particular for the current is important to have the control, because we need to avoid the overload. So the overload can be limited by limiting the current that is flowing in each branch. Calculation of the sensitivity coefficients. This is the usual Jacobian matrix. This is written in Cartesian coordinates, not in, we have implemented by using Cartesian coordinates. So the real part and the imaginary part of the voltages in every bus, not with a modulus and angle, but just the real part, imaginary part. So having this Jacobian matrix, you see that this is the sensitivity of the power with respect to the voltage, but if you took the inverse, obviously the matrix should be squared. We are not including just the voltage in the slack bus, that is the connection to the transmission network, because we think that this is fixed for us on the primary side of the substation. And so the matrix is squared, so you can take the inverse. And take the inverse, you have the relationship between the voltage and the power, active and reactive power. We can do also the same also for the tap in the transformers, because the sensitivity coefficients of active and reactive power at the buses to each OLTC variation can be calculated. So we have the relationship between the tap and the power with respect to the tap. So since we have the relationship between the voltage and the power, by multiplying by the product, we can obtain also these coefficients. For the current, since the parameters of the branches are known, And you have the sensitivity of the voltage. The current is the voltage difference divided the impedance. So when you know the sensitivities with the voltage, you can also apply for the current. No? So the equivalent is known, so the sensitivity coefficients for the current relevant to the branch current variation are obtained from the corresponding voltage sensitivity coefficients at the two terminals buses. So this is the structure that we have implemented in the computer model. So EMTP-RV is the environment that calculates the three-phase power flow. It is coupled with JavaScript in MATLAB, where there is the solution of the optimization problem, the mixed and integer linear programming problem, that obtains the variation of the control variables. So there is this iteration, and also including the sensitivity calculation, the sensitivity matrix calculations. And at the end, we have the updates of the set points. So in the idea here behind this model is that this algorithm it is, performs this calculation every 15 minutes, so updates the set points of the variables every 15 minutes during the day. It is appears to be reasonable. Obviously, for this calculation, you can use the updated forecast during the day. That will be much better than the forecast in the day ahead. So also, this is the case system that we have considered, a case system in which there is this are the two transformers with the high voltage network. So this is the substation, and this it is a system of 15 kilovolt, so medium voltage network, and there are two feeders that have the typical structure of urban feeders, so with very short branches, many loads and so on. And the other configuration is a typical rural network or feeders with long lines, and the load that is more dispersed. The thing that we have considered different scenarios, but I will show to you the results in which the production here inside it is quite heavy, and so there are several hours in which the flow, instead of going from the high voltage network to the distribution network, is going back from the distribution network to the high voltage network. So the power here, it is positive when this network consumes power from the high voltage network, and negative when there is this counter flow, the flow back. There are several units installed, so I will just describe the characteristic that we have considered just to justify the results. And these are the load characteristic for residential, industrial, commercial during the day. So in particular, you see that the load is big also in the evening, and there are several distributed energy resources, in particular distributed generation, also renewable. So we have considered 13 wind turbines, and also one photovoltaic field, 1 megawatt peak, and also dispatchable distributed energy resource that was very useful for the problem, because the more you can control, the better. So there are several distributed energy resources of different types, gas turbine, internal combustion, biomass included in the network. You see the values of the power that is limited. Since the network is 15 kilovolt, we cannot think about installation of several tens of megawatt. We need to be lower than 5 megawatt typically. Yeah, it can be 5 or 6, but not much. So this, these are the profiles of energy prices that are following the market, the wholesale market, with the this is the results for the first stage. So the dead scheduling, so cost minimization. So this is the scheduling of dispatchable distributed energy resources. Some of them are also combined heat and power units. So probably it is the thermal load that is the most driver for the dispatch. So you see that there are periods in which there is a very big production also in this period here, and this justifies the fact that the grid flow from the grid, this is just during the day from the dead dispatch. This is the profile that is expected in the power that is at the main substation. So when it is negative, so you see that there are several hours it is negative, the production is above the consumption. So we will expect to have problem of too high voltage. So the voltage will be too high, and we try to adjust this with the intraday schedule. So these are start the results of the second stage optimization. So every 15 minutes we have considered 3 options. In all of these we have neglected the losses, and I will try to show to you what are the effect of the losses on the other decisions, because in the first options we don't consider to take into account the power calculated in the day ahead. So we just consider how to minimize the voltage variations. So the objective is just the voltage variation. In the second way, we consider to keep both the voltage and respect the power of the previous day, the active power of the previous day, equally, so with the same coefficients. And the last one, it is a strange case in which we weight a lot the power, the active power of the previous day, but we can also move the reactive power. So we use practically only the reactive power and the tap change in order to control the voltages. I recall again the objective function. Now the results. I will put some of the results of this. These are just the power calculated in the dead, and these are the voltages, the profile of the of the voltage. For the urban feeder, we are considering 2 instants: the minimum load and the maximum load. Both were periods in which the power goes, it is negative at the substation, so the power goes from the distribution network to the transmission network. So these are the values in the 2 points, so minimum load and maximum load, and these are the voltages along the feeder for the maximum load. You see at for the dead scheduling, the voltage was very high, and then it decreases, and there are also 2 bands. It are clear more here. We have considered 2 bands of 1.5 and 0.95 per unit of the voltage. So you see that for our case, by using both varying the active power or not, the voltage is controlled. For urban feeder 1, urban feeder 2 practically has the same behavior, and this is for the rural feeder 1, in which you see that originally without the intraday optimization, the voltage in all the buses, in some of the buses, you see here in the x-axis there is the distance from the substation. So these are the various buses along the feeder. The feeder is a radial configuration, so there are feeders, there are points along the feeder in which the voltage is too high with respect to the rated value. After the optimization, this goes down, so the optimization is able to restore the voltage all along the line that is inside the band. So this also is for the second rural feeder, in which there is this behavior. In this case, the voltage was dropping, not too much was dropping, and the optimization can increase a little bit. This is a little bit interesting because both rural feeder 1 and rural feeder 2 are fed by the same transformer. So by using just the transformer, we have two different feeders that have a different behavior. One has an over voltage, the other the voltage is decreased. So if we act only to the voltage at the beginning, it is difficult to combine both things, and so it is important to have a control of the distributed energy resource of the generators that are connected along the feeders in order to stabilize the thing up. This is a table that I would like to show to you, to say for the losses. So the initial condition of the losses, you see that when you take into account only the voltage, also the losses decreases. But in the third case, in which the active power are fixed with respect to the previous day, also the losses decreases. This is due to the fact that the load that are considered in the power flow calculation in this three-phase are not constant power, as many cases we consider in transmission network practically. But in distribution network, we have seen that it is very important to take into account the fact that the consumption of the load is a function of the voltage. So there are loads that are more sensible, or sensitive with respect to the variation of the voltage in the various combinations. So we have taken into account this, and this is the effect. You see that for all the optimization, the mean absolute value deviation for all the buses in the network is reduced with respect to the previous one. We have seen also in the figure, obviously in the option 3, in which we keep the active power of the generators just equal to the previous day, the optimization, we have less capability of control, and so the variation is a little bit larger. Any questions so far? We can repeat the same also for the minimum load point. So I will just repeat this. This is for the minimum load, so the instant of the minimum load, the voltage, this is the urban, that is a little bit high, but not so much. It is improved, it is almost equal to 1, it's perfect. So the urban feeder 2, the same. And rural feeder 1, before the optimization, there is this over voltage in at the end of the feeder, and the improvement with the intraday scheduling, and also this is the and this is the rural feeder. I make a mistake here. It is a rural feeder 2, Yeah, the last one. I do apologize. This was a rural feeder 2, in which there is here an overvoltage, and it is almost compensated. There are always some difficulties. So you see that also here the fact of the losses, in particular the case here that the losses increase when we keep the active power equal to the head. We have seen that here the optimization tends to decrease the active power. So decrease the active power, decrease also the flows into the network and so on. By keeping the active power equal to the scheduling, we have also this effect. The mean absolute voltage deviation, it is decreased with respect to the initial condition. Do you have any comment about this? Do you think that is reasonable? So in brief, the intraday scheduler, based on the iterative solution of a simple linear programming problem, allows a detailed representation of discrete tap position into the transformer and the incorporation of the line ampacity constraints. An interesting feature of the proposed approach is that at each iteration, the linearization of the optimization problem is achieved by means of sensitivity coefficients that can be directly obtained from the results of the single power flow calculation. Obviously, we have tried to discover in the manual of the software how to extract the Jacobian matrix. That was the key. But it is good. It is in general provided if they are using thorax. Good. The charging station. Do you have any questions? So
this MILP three-phase power flow.
It is a three-phase power flow. That is.
Is it the tool which we are using, or we have to write any algorithm for that?
No, we have used something out of the shelf, they say, no? That is the EMTP. EMTP has a power flow calculation at the beginning, and we have used just this one, that is the steady state, because then the electromagnetic transient problem has a transient. But in this software, there is the first calculation, the steady state. So the steady states, we have used this, so it is already done, and it is implemented by using the iterative solution of this power flow.
So it is a readily available tool in the EMT software. Just we have to use the tool.
Yes, it is.
We have to feed the inputs and we have to get the output.
Yes, the thing that we have done outside the tool, I can show to you again the scheme that is useful, not to say it is nothing special, but just to say it is this, that is EMTP as the three-phase calculation. And then from this, the solution, we take also the Jacobian matrix. So we have implemented a script in JavaScript that is connected to EMTP, and in order to calculate the sensitivity matrix. Then we prefer to solve the optimization problem in MATLAB. So the JavaScript calls the model in MATLAB that solve the optimization, and these variations are given back to the calculation of the power flow. And this is iterated until the decisions in one step and the other iteration are the same, or with a small variation, so we don't change anything. And in general, it converges in few iterations, 5, 6 iterations converges. So since the calculation is just a fraction of seconds, it means that in few seconds you have the solution. And in this way, you have, you are certain that you obtain a feasible solution, because, it is the power flow calculation that is there, until the power flow calculation converges, but in general.
So works for both radial and meshed loop networks.
Yes, can be also done for the loop because the power flow it is Newton-Raphson, so it is the same calculation. No, EMTP can be used also for the transmission network. Also, we are using a lot for the transmission, so it is. It's not depending. Yeah. No.
How is time synchronization between EMTP and MATLAB?
Pardon me?
How it could be possible with the time synchronization between ETAP and MATLAB?
Okay, it is not very much important. I will show to you after something that is, this synchronization is more important something. But here, it is every 15 minutes you calculate the power flow. This JavaScript is also used in order to couple the model that is implemented in MATLAB. And so this takes the Jacobian matrix, calculates the sensitivity, goes to the problem, calculate, and then this recalculate the distribution, the power flow. So, yeah. So the
synchronization leads to some error by giving input and output results.
This is not a time domain simulation EMTP. It is just a power flow. So it is a steady state.
But our solution relevant to 15 minutes time frame solution.
Yes, we need to have this
We have to
optimization.
our solution between 15 minutes result, synchronizing with MATLAB and ETAP result.
The EMTP is not a time domain simulation. It is just one power flow. So we are just optimize the things every 15 minutes to give to the real network the updated set points. So this is quite, there is a synchronization but it is quite easy because it is, like a traffic light, no? So it is calculation and then optimization. But when we do the optimization, this is idle. No, it doesn't do anything. And then we redo this calculation and iterate, and we iterate until these set point updates are varying. If they are stable after two different iterations, we have obtained mostly the same result. We don't continue to iterate. Just
Sir, how to insert all these renewables, distributed generation, just like wind turbine, solar, how to incorporate
into the system?
If a feeder, with 120 feeder bus system,
Yes.
for example, those contain, solar is also, energy is also there. At the same time, wind energy is also is part of that.
Yeah.
In that condition, how to consider those PV systems?
Yes, these are considered in this way here. In the power flow calculations, we expect that in the 15 minutes you have more or less a better forecast on what happens in these plants. It is not every second, but in the 15 minutes, so you say, okay, from 15 minutes, the power from these sources will be at that level. So we are considered as an injection in the nodes in which the power stations are connected.
So you only consider the injections?
Yes.
Not the, there is no such modeling of those sources?
No, they are considered as PQ buses in the power flow. In general, we have considered there is no the capability to change the reactive power in these simulations. Nowadays, some of these, at least the big photovoltaic station and also some wind turbines have the capability also to control the reactive power, and this is something that can be offered to the distribution system operators to adjust the voltage. So it is included in the so-called dispatchable energy resource, at least for the reactive power.
I think you use some 15 wind turbines.
Yes, yes, we have included this in particular in the rural area in order to represent the fact that in some parts, also of our country, in the countryside and so on, there are particular conditions that allow also to include these small wind turbines. I would like to show to you also the second model, and then we can also take a 5 minutes break up. I'm going. I do apologize. Probably it is better that I'm using this. Okay, this was the other thing that I prepared for this introductory lecture hour. It is the idea of having in the urban area parking lots with many charging stations. And we have considered charging stations that are fast, so the 50 kilowatt. Nowadays there are also bigger, but we have limited to 50. And we have considered several, so in these parking lots. So the idea was how to, design some kind of protection or intelligent device, electronic device, and so on, in order to protect the feeders and also limit the stress to these distribution transformers from this charging of the parking lots. Okay, in this case, this synchronization is the key point, because we have two things here. We have the power system, we have the electronic device, and we have also the communication networks that it is needed in order to send the information inside the network. So we have implemented a co-simulation environment in which there is the simulation time domain of the distribution network and also a simulation in time domain of the communication network, so the telecommunication network. But we wanted to do something more detailed, and so in order to better study the thing, we have also included a simulator of the traffic into the city, so the traffic, by assuming a different percentage of electric vehicles with respect to combustion vehicles. So all the three tools needs to be, synchronized, as they mentioned, because they are all in time domain with different time steps, so they need to be synchronized. I would like to show to you this experience. So we focus on parking lots in urban area. The set of electric vehicle supply equipment, these are the charging station of each parking lot, are fed through a medium voltage, low voltage transformer that represented the grid connection point. So we focus here not on the low voltage, but the medium voltage. And because the low voltage is just limited into the parking station. And we analyze a multi-agent, they say, system composed by intelligent electronic device, so a special protection installed in the substation, high voltage, medium voltage substation, and in correspondence of critical network branches at the beginning of each feeder connected to the secondary side of the substation, for example, that may be overloaded due to the electric vehicle charging. And also distributed agents, so a control in the parking lot, control units connected to the shared communication network, so each associated to the cluster of the charging units in the parking lot. So we can think about a device in the substation that measure the overloading, so the current in the transformer or in the branch, and a control in the parking lot that they receive the signal from that device that says to him, oh, you need to decrease the power to this charging station. In general, these charging stations are equipped with the possibility to control the maximum power. So they are rated 50 kilowatt, but they can operate also at 40 or 30 or at 20. So there is the possibility to limit the power. So this control in the parking lot can decrease the maximum power of the charging station if there are some events into the networks, no? Much other load, so that the feeder is overloaded. So the idea is that this device, the transformer, measures the current, compares such a value with the maximum operation value of the line and the overload state of the transformer. Each device is able to communicate a congestion index over the cellular network that denotes whether and how much the corresponding power components is overloaded. The agent associated with each cluster, so at the parking lot, is able to control the charging power according to the received congestion index. So we have this. Is it resumed? The idea behind is how to control this congestion index and how fast we can send these messages and so on. We don't want to stop charging, but just charging with less power during the transient that is needed from the network. So one agent per each transformer feeding a cluster of electric vehicles. The device measures the current value and compare with the maximum line operation. So there is this idea to implement a kind of a proportional integral control. So we have this signal that is, with a coefficient, amplifies this error that is, you see, a function of the error in the current. So if the current is larger than the maximum current, divided the current maximum, this gives to you the error at this time, and take into account also the error in the previous time step. And there is also an integral part in which the two errors are summed together. So there is an effect that if the error is just in one period, okay, you take one decision, so you reduce a little bit the power. But if it is the second period in which there is again this error, this accumulates. So we need to decrease more, or to increase more this signal, this congestion signal. So as long as there is this error, this signal, congestion signal, tends to increase. The idea is that for the components, an overload for just a few minutes, it is not so important. If the overload continues in the time, so thermal effect, or the degradation of the cable, of the transformer, the effects are increased. So if the deviation is just for a short time, also your congestion index is limited. But if the error continues in time, so the congestion index increase. Why is increasing? Because there is this effect that this signal goes to the controller of the parking lot. And the controller of the parking lot sets the maximum value of the charging station with the value of the charging station divided this signal index. So the higher the congestion index, the lower also is the power. Continuous. So it is a continuous the area. We are in the loop of the control in order to represent this, the platform that integrates the mobility simulator to reproduce the mobility, just to have a study on what happens in the city and in the distribution network of the city due to this effect. And we have considered Bologna, so it is a small town of 300,000 inhabitants, power distribution network simulation, EMTP again, and a simulator of the wireless communication network. These are, the tools that we have used. This is EMTP, so it is the simulation of the distribution network. This times in during the day, so varying. This is the model of the communication network, and this is the simulator of the urban mobility. In which we can also decide how many electric vehicles are used. They are also using the information provided by the municipality of Bologna, so it is representative of the traffic flow in the city during the day. So this is the mobility simulator, an simulator for analysis of traffic, including electric vehicles, and it is in general used by the municipality to understand how to change the rules into the city in order to reduce the congestions, and so it is based on these tools, OpenStreetMap and so on, accurate modeling of the city scenario, modeling of the control of traffic. It is tools. We have implemented it by using these tools. Yeah.
2015, latest also it may applicable.
I have not understood the question. Sure. So we have
mentioned some tools, Sumo, many.
Yes, this is also free, because in the network there is in internet. This is open source. The difficult thing is to have this data and so on, but they are provided by the municipality, and we have tried to use them. They are collected also in the sensors in the streets, and they know the number of vehicles that are running. There are some assumptions there. And so the assumption is that I also mentioned here, probably I can go directly in the test case. And I will come back to see the thing, but the idea is that a first simulation that we have done, we have a first case in which we random generation of 200 events. Events are the path into the street of a car. So there is a vehicle, and we have chosen every 5 seconds for a part of the city that I will show to you after, with a 50% of probability that each event is associated with an electric vehicles, or obviously in Bologna there are much less electric vehicles than this, and every time a vehicle leaves the simulation and reaches the destination, the new event is generated. So it is randomly chosen when there is the appearance of the vehicle and when it is the destination point. I don't know if this answered the question. Yeah, a little bit. I can also show to you better but we don't know exactly which is the destination of it, or it is just a random, and trying to follow a little bit the traffic. the power distribution simulator, the only thing that we have included developed in the model is the charging. It is the model of the charging station. So it is representing the fact that there is here a consumption of active power when there is a car from the simulator of the urban traffic that goes into this specific parking lot. So every time the urban simulator, the traffic simulator says to EMPP, oh, there is a car connected, then there is here a load that is activated and represent the consumption of that car. And in the model, obviously, there are also the other loads. So during the period, we have done also the simulation for 1 day, there is the usual profile of all the other loads into the network. So in each instant, you can measure to have the value of the current in the specific branches or transformers. This is the idea. So this is the problem of the data exchange. So there is the model of the urban traffic and the model of electric power system. Obviously, there is an initialization at the beginning, and then the traffic simulator has a delta T of 100 milliseconds that starts of charging individual EV at a specific charging station. It sends this information to the transient simulator. So when this goes for 100 milliseconds, this is stopped. So there are this signal. So and then it is running with a delta T 1 millisecond. So the simulation here in the distribution network, it is 1 milliseconds. We don't need to represent the details of the transits, but just to have the average value of the so we decrease the computational time with a discretization of 1 milliseconds for the distribution network. So and then do this thing and send the message here in order to start again the model, the traffic simulator for 100 milliseconds and so on. So there is this synchronization between the two. Description of the test case. It is, this is the map of Bologna. There it is a little bit. Here there is the map of the charging station or parking lots in Bologna now. We have only select some. Obviously, they are not equipped with many charging stations of 50 kilowatt, very rare, but we have added in the simulation. So we have considered just a part of the city in order to decrease also the computational effort. So these 4 parking lots that are connected to two feeders here in the medium voltage station. So you see that these are the clusters, the two 15 kilovolt feeders, and the main substation. It is also indicated here. And we are in the center of the city. And this is the representation with the antenna of the communication network based on cellular phone. So these are the details with the feeders, medium voltage, the antenna of the cellular phone, the area, and the connection to internet. The traffic simulator generates a flow of random events representing a specific trip of a vehicle in the city. For the case of electric vehicles, when the state of charge of the corresponding battery is below a threshold. So in the traffic simulator, we represent also the level of energy in the battery. It is below a threshold set to 25%. The vehicle deviates from the planned journey and reaches the closest electric vehicle charging station unit available. The first test case represented the 200 events that I mentioned before, and perhaps we can also see some results. So these results, there are connection here of the number of vehicles connected in the parking lots. There are 4 parking lots, so you see in the time this repeated connection. You see here the congestion index for the parking lots. I will be back describing this a little bit after. I would like to see here which is the behavior of the current in the transformer. So at each connection there is a peak of the current that increases because there is the connection of the vehicle. But then there is this congestion index that is sent to the controller of the parking lot. So you see that in times of here are seconds, no? Because it is 20, 420, 440, so it is 20 seconds. So in the matter of seconds, the controller of the parking lot decreases the total power that can be provided by the charging station there. We are not focusing on which is the charging station that is, decreased. They are decreased all together. So there is another connection, and then the action of the congestion index that decreases the current. Then there is another connection, and then probably there are no cars that are connected here. So the current decreases until there is another connection of another car and so on. So you see this for what are these values? We said, okay, this is working if you consider that the message is sent and received instant without any delay. But there is also some communication delay and so on. So we have considered 2 things. One is the background traffic, so the different level of background traffic in the communication network. So that means delay, latency, they say, in the communication channel. So different levels, and you see different levels, it means that also the control is a little bit delayed. And also the block error rate, so which is the percentage of the communication packages that are lost in the communication channel. So they are not received. 0, it means perfect, all the packets are received, and 0.1%, it means that 0.1% of these packets are not received. So the device in the transformer continuously send this information spread, so it is a broadcasting of signals, and the controls they receive. We have done also the simulation for the entire day. So in this figure there is a time in the x-axis. In the y-axis there is the number of vehicles, and here the maximum power in the charging station, that is 50. So you see that when the number of vehicles connected is low, the maximum power allowed by the controller in the parking lot is 50 kilowatts, so it is the maximum. But you see that there are hours in which the number of cars parked in the parking lot is quite high. So it means that there is a congestion into the transformer, also due to the other load into the network, because the network is not serving just the parking station, the parking lots, but all the users. So in these periods in which there is a connection, in which there is these congestions, this signal decreases the maximum power of the charging station in order to avoid the overloading. This was for feeder 1, and this is for feeder 2. You see that the important aspect, and was also the reason behind this work, is how much is the percentage of electric vehicles that cause problems into the distribution network. So you see, if there are only 5% of electrical vehicles with respect to the total vehicles of the city that are electric vehicles, there are practically no problems. There is just a reduction here and a little bit reduction here. And the solid line, 10%, you see that also today there are some periods in which there is a problem into the network. This was the idea behind this, because we don't know how fast the use of electric vehicles will increase in the future, so it is difficult to plan the distribution network in order to allow the charging of all the vehicles that are expected, because we don't know. So the idea is to implement into the network some protection or control device that allows the present distribution network to cope as far as possible the new request, and then postpone the reinforcement to the network when the expectations are more sure. I don't know if you have any question or comment in this. Because if not, we can go to the second part, but probably we can also take 5 minutes break. Good. The second part is for the voltage control.